Present it again. I don't need to introduce myself. I'll save some time. So actually this is the hybrid simulation of bridges with two projects about hybrid simulation of bridges with innovative column designs, and actually they are projects in progress. They are ongoing. And here Yingjie Wu is the PhD student who is working on this, and Professor Selim is the PI on both of them. And I'm working in the projects also. So Yingjie couldn't be here because he needed to do a couple of things in Davis Hall, and that's why I'm presenting it. So the outline, basically I'll make an introduction, and then I'll talk about the first case, which is the hybrid simulation of a bridge with the so-called V connector, and the other one is the hybrid simulation of a bridge with self-centering, rocking, and energy dissipating columns. So this I have shown this in the morning lecture also. I mentioned analytical substructures are those that you know how to model, and experimental ones are those that you don't know how to model properly. And considering the innovative column designs, there is generally limited data about these, and also, so therefore we want to investigate the response, right? Because we don't know how it will behave. But it's practically not possible to test a complete bridge. And also one thing related to this recent collapse in Miami, the bridge collapse, you never know how new methods or new materials work, so you need to test them, test the materials or the designs or construction methodologies. So therefore, since it's not possible to test the complete bridge, hybrid simulation is a great tool to simulate the seismic response of bridges with innovative column designs by modeling the columns and or the innovative parts, and by testing the innovative parts in the lab and modeling all the rest. So the first application is the hybrid simulation of a bridge with a V connector. So what is this V connector? Basically, this is a cross-section that shows the device. It's an innovative connecting device that is designed as the joint between the column and superstructure, or between the column and footing in a bridge. So how it works is basically you have this V-cone that is, let's say, embedded in a column, and that houses this rod. This rod, and the other end of the rod is connected to the superstructure through the hinge connection. And what happens is, ideally, this rod deforms elastically, and therefore it produces sort of an isolation layer. And similar to any other isolation, this basically elongates the period, and the objective is to make sure that other bridge components are elastic. So it's, and then also it enables accelerated bridge construction and rapid retrofit or replacement. And so this, to do the hybrid simulation, first we start with an analysis, and then we select a prototype bridge to move on. And this is a prototype bridge that was selected from Northern California. And this is basically a single column, two-span bridge band, and this is suitable for hybrid simulation because we can test this V connector and model all the rest of the bridge as the analytical substructure. And so, as I mentioned, we start with modeling this analytically, and basically the V connector, since it's between the column and the bridge deck, that comes in as a component here between the column top and the bridge deck, and we basically use translational springs that represent the force displacement relation of this V connector. And also, because there's a hinge, we use a flexural connection with zero stiffness to provide to simulate that. And the force displacement of this V connector basically is something like this, that consists of some friction and when the friction is overcome, the rod starts to deform elastically, and this second branch is basically corresponding to the elastic deformation of the rod. And this is modeled using two translational springs in open Cs. One is linear elastic, that is for the rod, and other portion rigid to plastic that corresponds to the friction. So actually I forgot to mention that the friction is really quick, provided by this the washer here, and this basically this plate and the washer, they touch each other, and then that provides a friction surface. Okay, so and here as I mentioned, we want to keep the column response elastic. So, and to keep the column response elastic, the stiffness of this V connector needs to be reduced because of two reasons. One is reducing the stiffness increases the effective period of the bridge, and that reduces the accelerations and according to the inertia forces. And the second reason is when you have smaller kV, maximum force of that the V connector experiences gets reduced, right? And since there is equilibrium between the V connector and the column top, the force that the column experiences gets reduced also. And to make sure about elastic column response, we did some analysis using some ground motions, and this is just a set of ground motions that has been used, and actually it has been used previously in a test from the researchers at UCSD. And this shows some analysis results for a stiffness of 100 kips per inch. This shows the column base moment curvature, so it's not elastic column response. And this just shows the V connector force displacement response. It basically, I plotted here to show that it behaves the way that we modeled it. And therefore, from this we understand that we need to reduce the stiffness because we want the column response to be elastic. So we reduce it to 30, and then we see that the column response gets elastic from these result of 8 ground motions. And then this is the reconnected displacement here. Obviously, one disadvantage is when you have that, the displacements increase, but that's the same thing as if in any other isolation. And we tried one more case, 20 kips per inch. It's similar, but and here all the analyses were done considering a coefficient, friction coefficient of 10%. And so for practical reasons, so this shows the forces and deformations for these 3 different cases. For practical reasons, we chose the V connector with 30 kip per inch as the most suitable choice, because if you reduce the stiffness a lot, your rod size gets smaller, and that can have unintended consequences and all that. So therefore, V connector is designed according to this desired stiffness and friction values. And to accommodate the lab loading equipment capacities in the lab, V connector is basically designed to be a 1/3 scale. And here the test plan consists of 2 phases. First is the cyclic. As I mentioned, we have a force displacement relation, but it needs to be validated before doing any hybrid simulation. Therefore, this first phase will be used to validate that force displacement and to inform us if we need to make any changes in the hybrid simulation setup. And the second one, as I mentioned, we'll have this bridge model, everything modeled in the computer, including the column, and we will only test the V connector. And so actually this is a great setting for hybrid simulation because we don't need to model the column. We can only test the V connector, and if the behavior is not as intended, we can easily change that and make a new test. So hybrid simulation is a great benefit for this type of testing. And actually this first phase and the small level hybrid simulation will be done on Monday. or maybe this week. Not this week. Okay, maybe Monday. Yeah, we'll do it on Monday. And this shows the test setup. And here you see that the V connector gets connected to two concrete blocks, which are actually huge blocks and which are heavily reinforced, so that they remain elastic and they don't deform. And we put the V connector in between two blocks. And these two columns on the plan are used to apply the lateral displacements, and vertical actuators are basically used to apply the gravity forces. And yes, okay. So these are just some slides that show the reinforcement details of these heavily reinforced concrete blocks. And so there is a construction sequence. So this V-tube basically gets placed in the reinforcing cage first, and then the concrete bottom block is cast, and then this bottom block is connected to the stone floor, and then yes, okay, so then the top pad with the hinge holder is placed on top of this bottom block, and this rod and the hinge is placed through this hinge holder. Then there's a nut that fixes the top of the hinge from the top, and once all of these are ready, the top block is lowered, and there's a hole in the top block that the hinge would go through. And the final step is the nuts are tightened from beneath, and eventually this is the section cut. This has been completed, and it waits to be tested. And I just want to highlight some of the hybrid simulation details here for the second phase. So as I mentioned, the connector will be the experimental substructure, and all the rest is simulated as the analytical. And we'll model the column inelastic response. That will be part of the analytical model. But since the column is designed to remain elastic, we are not testing it. We assume that the column is the elastic portion that can be modeled. But just to make sure that it really stays elastic, we'll provide the inelastic response to see whether it stays in the elastic range or not. And we'll use this alpha operator splitting integration method that I mentioned as convenient for hybrid simulation. And since it's 1/3 scale, the computed displacements will be scaled. They'll be divided by 3 before applying it to the specimen, and then the forces will be multiplied by 9, which is S² according to the simulative relations, before getting used in the numerical integration. And we'll use OpenFresco, and Andreas mentioned that OpenFresco can do these scales, so we'll use that feature. So okay, this was the first one, and the second application is this hybrid simulation of a bridge with self-centering, rocking, and energy dissipating columns. And this is basically a collaboration between UCSD, where the PI is Jose Restrepo, and UC-Berkeley, where the PI is Professor Selim. And so UCSD part was basically design the column and do a shaking table testing. And we'll do a hybrid simulation version in here as our part. And so this I'll show the innovative design features of this set of columns. First is the self-centering with post-tensioning bars. And then there's a steel jacket used for confinement. And also there's also energy dissipation through rebar yielding. So, and rocking is also allowed at the column base. So it's a combination of rocking, self-centering, and energy dissipation. That works pretty well, actually. And for the first phase, which is the shaking table test, they are already completed, and the blind prediction competition is organized from these tests. And these are the set of ground motions used in the shaking table tests. And here I will show this video. This is actually created by Arpit Nema, who is this UCSD student working on the project. So this, actually you can see one of the large tests, and then you can see really large drifts, and eventually the column comes back to the center, so it's self-centering. And here you see the force displacement, you see the energy dissipation plus the pinching type of thing, which is actually the self-centering. And this one is a similar video that just shows the rocking from the column base. Again, this Arpit prepared these. You see the rocking. Okay, so this basically shows the residual drifts. Here, the white parts show the residual drift, and the gray parts correspond to the peak drifts. So as you can see, for really large drift ratios of up to 8%, there is little residual drift. So then this worked completely as intended. So then I am moving on with the hybrid simulation. There will be two sets of hybrid simulation. First one will be exactly mimicking the shaking table test. So in the shaking table test, we have these mass blocks that are used for the mass, right? So in the hybrid simulation, we will replace these mass blocks with the analytical mass, and everything else will be the same. So we'll basically have a band with the analytical mass modeled in the computer, and we'll compare the shaking table test results and the hybrid simulation results. So that will be the first phase, and then actually shaking table tests were pretty useful for setting up the hybrid, because from the shaking table test results we observed that the moment at the top of the band cap is negligible. So since the moment is negligible, then as I mentioned in these substructuring slides, we don't have the rotational degree of freedom. So therefore we can only use one horizontal actuator. And yes, single actuator is used to apply the lateral displacements. And as there is a vertical component of the ground motion, which was applied in the shaking table test, we will also apply them in the hybrid simulation. And we will use this vertical actuator actually to apply the forces due to gravity plus the vertical component of the ground motion. And what else? In the second phase, we'll move on to full bridge modeling. So this will be the experimental part, which is the band, the band itself, and then the bridge deck and the abutments and all that will be modeled in the computer as the second phase.
Thank you.